All right, well, good evening, everyone. We're about to plunge into our next chapter in our general class studies. We'll be in chapter 6 tonight on digital modes. So there's a lot of, I discovered as I was going through this that there's questions scattered all over the book on this, or all over the groups in the question pool. But the ARRL did a pretty good job of condensing it and bringing it all together to put it into a teachable sequence, which I've modified a little bit. There were a ton of changes between last pool and this pool. The technology and the physics, of course, stays the same, but they change pool questions and add and delete and modify, and we have to get all of that stuff updated in our materials, which hopefully we've done. All right, well, we'll go ahead and jump right in then. Just before I do, though, I wanted to comment about digital modes needing to speak the same language. So I found a Far Side cartoon on my daily calendar that I thought was very applicable to what we're going to be talking about tonight. And there it is. Hopefully it's readable. So this guy's trying to talk to his duck. And he tries all different languages until he finally finds one that works. And then look at him go. Well, digital modes are a lot like that. Yep, the transmitter and receiver have to understand each other. All right, well, let me jump over to the presentation. Chapter 6, there's 5 sections in this chapter. Starting off with the basics. So a long while ago, I think we talked about single sideband and AM. And I brought a picture back up here because it has some applicability to what we're doing here. Digital modes are treated as voice modes as far as FCC is concerned. And we've got a picture here of basically an AM signal carrier, got an upper sideband and a lower sideband. And some of the digital modes use the lower sideband for all bands. Some use the upper sideband. We'll get to that. But the thing I wanted to kind of prime our thinking about, if we have tones, if we send let's say a 2000 hertz tone on upper sideband, let's say it lands about here, and a lower frequency tone would land over here. So the frequency spectrum goes from low to high. But on lower sideband, it flips. The lower frequency tones are on this side, the higher frequency are over there. So if we get the sideband wrong, it may not be possible to decode what's being sent. So that'll come in a little bit later. So as we mentioned, digital modes are regulated as voice modes by the FCC. That implies that nothing is going to be wider than 3 kilohertz, which is our single sideband bandwidth. And we have to somehow, now digital means ones and zeros, so somehow we've got to get the ones and zeros translated to something that can go out as single sideband voice. So we have to translate the ones and zeros to tones. Here are some common modes here that are part of the WSJT suite of programs. Much more on that later. And most of you have probably heard about D-Star, System Fusion, and DMR. Those are all modes that are popular on 2 meters, but only if you've got access to a repeater or connection someplace or a hotspot. There are some HF modes as well. It's interesting that slow scan TV, which we're really not going to talk about in the general class, but that's also sent as audio tones and fits within a 3 kilohertz channel. The cool thing about that is if you get set up for any digital mode, you can do all of these things, including slow scan TV. So next, how do we get digital ones and zeros converted to tones? We'll check that out next. And as mentioned, we have to fit within a 3 kilohertz space. The data rates and bandwidths are specified by the FCC. And rules and regulations thing, digital codes have to be public or we can't use them. We can't do any secret agent man stuff here in ham radio. unless you're controlling a satellite, or there's a couple of exceptions. So sound card, for a lot of people, this is mysterious, because you'll see the term sound card come up all over the place in digital. Some of you know what this is, and some don't, so I'll kind of go over it and some of the variables. So we have a picture here of basically an old-time sound card. Actually plugs into a computer. Don't see that very much anymore. So data is ones and zeros, audio is analog. Since we have to have tones or something that would modulate a single sideband transmitter, we've got to somehow get digital to analog conversion to get from our computer to the radio to be transmitted, and then back the other way from our radio's receiver. We're going to need to get that audio sent over to the sound card in order to be converted to digital for the software to operate on it. So the parallel here, if you consider playing an audio compact disc or a microphone input to a computer for like a recording application, we can kind of see the parallels here. A compact disc has pits in it that are scanned, and those are in the form of ones and zeros. That digital is then converted to analog, and it comes out the speakers on your computer. So that function exists within your computer. Or if you've got a microphone recording amp, it goes the other way. The microphone goes into the computer, it converts that voice to digital, and stores it on the hard drive. So both of those paths are very useful for ham radio. So the same sound card that does that conversion can also be applied to amateur digital modes. There's one little trick that has to be done, though. The computer is assuming certain pathways from those digital sources to the analog, so we have to use an audio driver software to tell the computer, no, we don't want to send this audio to the speaker or send it to the hard drive from the microphone jack. We want to send it to the radio. So the reprogramming of those paths is what's accomplished by the audio driver software that you normally have to install when you're setting up for a digital mode. So where might one find a sound card? Well, inside the computer, if it's one of these old style. It can be an actual sound card inside the computer. More often it's a chipset on the computer motherboard. You can have an external digital interface. A lot of you have heard of the signal link over here. It's one of the most popular. There's various other manufacturers as well. Some people like the external sound card even if they have an internal one because it's got knobs on it and you can adjust levels without having to search through menus. And then finally, the sound card, quote unquote, can be inside the radio. And of course that would be a chipset in that case. But the function of the sound card is inside the radio. The advantage of that is that the only connection you need to make between the computer and the radio is a USB cord. That makes it very clean. So where can we find digital activity? Well, our book gives us on page 6-2, it's table 6.1, but you don't really need to look at it because I've reproduced most of it right here. It tells us where we can look. Now this is in a generic sense. This isn't just FT8 or radio teletype. The digital modes are kind of grouped together on the band, and we can find the specifics in the band plan documents. I've highlighted one item here, 20 meters, 14070. That's going to be useful for a couple of pool questions. The old pool had several, but now we only have to worry about 20 meters. It's kind of fun to listen to these digital modes. If you've got an HF radio, you can tune around and try to see what some of these things sound like. Or if you don't have a radio, the WebSDR resources are a way that you can listen on the air, because some of these modes are quite interesting to listen to. Now I've put up this chart of FT8 frequencies. FT8 is all upper sideband on all bands. And there's a couple of reasons I wanted to put this up. First of all, if you're interested in knowing what bands are open at any given time, what I've done on my radio is I've put each one of these frequencies in a memory location. And then just as fast as I can turn a knob, I can see if 160 is dead or 6 meters is dead. Very quickly I can tune. If I hear any digital activity on any of these frequencies, say, oh, that band might be worth nosing around in a little bit. I put a couple of arrows in here. These are the 074s, including 20 meters. An arrow here because there's a couple of pool questions that will touch on that. And even if you're not interested in using FT8, some people are not, it's really, really nice to have the software so you can see where signals are being decoded, or what parts of the world you're getting decodes from. So if you're getting decodes from Europe on 20 meters and your favorite mode of operation is single sideband, you'd have a pretty good chance of working some DX on 20 meters. So FT8 can be very handy to find out what is open. Now there's a question that asks which of the following provide digital voice modes. And what they do in the pool question is they list several modes that are not digital voice, and they want you to be able to recognize that DMR, D-Star, and System Fusion are indeed digital voice modes. I've added a little bit here. You expect to see these on 2 meters and 440 primarily. And I think the reason for that is because every manufacturer that's out there has got radios that are dual band 2 meter and 440. So there's a large population that would be using these. These modes work at 4,800 baud, and I think Gary may have mentioned in his rules and regulations chapter that we can only use up to 300 baud below 28 megahertz. So none of these three would be usable on HF. They're most commonly seen on VHF and above, although technically they would be legal on 6 meters, but I don't think too many people use them there. And these aren't tremendously useful if you don't have a local system you can connect to. Then there's a couple of options for HF. AOR's digital voice and free DV is another one. I don't know if anybody's played with that. Here we got a guy screaming into a microphone, creating digital somehow. Frequency shift keying, all right? We're jumping around a little bit. I've got a picture over here, spectrum display, and we see these two little peaks right next to each other, and here and here. This might be something that you would find very common in an RTTY contest. And what you're seeing there is two frequencies that are being transmitted, or they're bouncing back and forth between the two. And those frequencies happen to be 2125 and 2295, so they're fairly high tones. And they're spread apart by 170 hertz. We're going to talk more about that as we continue on. But in terms of what you need to know, direct binary FSK field strength. How about frequency shift keying? Generated by changing an oscillator's frequency directly with a digital control signal. So we're actually sending ones and zeros from our radio to our transceiver, and the transceiver has the capability of saying, okay, this is a 0, I'm going to send this frequency. Okay, we switch to a 1, I'm going to send something that's 170 hertz off from there. They're actually moving the oscillator frequency for direct binary FSK. The two frequencies are known as mark and space. And the origination of those terms back in the good old days, way before my time, they would have teleprinters that If the signal was present, it would actually lower a pen onto a piece of paper, a paper roll, and then when the signal went away, they'd lift the pen, and that was the space. So that's where mark and space originally came from. The old teletype, or the old telegraph systems, I should say. So we've moved through that, and we're right into some questions. All right. Now I gave you that little trick to think about. Number, in what segment of the 20 meter band are most digital mode operations commonly found? And anybody can unmute and venture a guess.
D.
It is D. That was, remember I said if you could remember the 070 trick, that would answer several questions. And this is where most digital mode operations are commonly found. FT8 just happens to be right on 14070, but the other digital modes go up from there. Which of the following provide digital voice modes?
Delta.
Bravo.
Delta.
Okay, digital voice. Digital voice is.
Oh, Delta.
Got it, yep, very good. Some of these things you haven't heard about, we haven't talked about yet, but it is delta, the digital voice modes. How are the two separate frequencies of a frequency shift keyed signal identified?
Delta.
Delta, mark
and space.
Mark and space, yep. How is direct binary FSK modulation generated?
Bravo.
Bravo. Okay, and there is a little memory trick here. You'll notice the word direct here. The only question that has the word direct in it, or the only answer, is this one. All right, we're moving right along. Now, character-based modes, the upper level concept here is a character-based mode can be thought of as a keyboard-to-keyboard mode. If I type the letter A on my end through one of these modes, a letter A will show up on your end. So if it was teletype, I'd press the A key, and your software would convert that to an A and put it on your screen. So that's the concept of character-based modes and keyboard-to-keyboard communications. Okay. Radio teletype originally used teleprinters. These good old machines here, military used lots and lots of them. And hams still use a radio teletype, but rather than these mechanical machines, now some people actually restore these and put them back into operation. I was at a ham fest where they had a whole bunch of these different models all set up and actually functioning. It was just fascinating to see. So it's still in use on the amateur bands, but rather than these, we've got software that will decode signals off the air and present them to us. Another one is PSK31. PSK31 was a mode, the first sound card mode, actually. These started out as mechanical machines, and then hams would build or buy what are called TNCs, terminal node controllers, to interface the machine to the computer. Now with PSK31, all of that is built into the software in an application. And I thought it would be kind of neat to show, most of you have probably heard this before, but I'm going to see if I can just play some of the sound. You used to hear them on news broadcasts back in the 60s.
It did not quite.
It will in a minute, I hope. I can't hear it here, but Gary Carey told me it's going out. Does that sound familiar to anybody? All right, we'll kill that. This. All right, some definitions at this point. Bit. What does bit stand for? Does anybody know? Bits are ones and zeros, but what does bit stand for?
One bit of information, either a 0 or a 1.
Well, that's true, but the origination of the term, it's binary digit. that was shortened to bit in a binary digit will be a 1 or a 0. I thought that was some interesting history. Now, bit rate, this seems kind of obvious, number of digital bits per second sent from one computer system to the other. Like 300 bits per second or 1200 bits per second. There's all kinds of rates. You notice I've got a picture of a dictionary here. That's what we're doing. What is a symbol? A symbol is a characteristic of the transmitted signal that represents data. Now, symbols sent and bit rate are not the same thing. I'll have an illustration of that coming up. Now, baud is the number of symbols per second, also known as the symbol rate. So baud and symbol rate are the same thing. So we've got a bit rate and a symbol rate. And here's an analogy that will hopefully help make this clear. If you hold up one hand, that's one signaling event or a symbol. But you've got multiple digits on your hand. You've got 5 fingers. So one signaling event can represent 6 states if you include the closed hand, 0 through 5 fingers. So I might hold up, let's assume that we're in a noisy room, party, and your friend across the room is watching you, and you hold up 2 fingers. That will tell your friend that you want a cheeseburger. If you hold up 3 fingers, you want a cheeseburger and a Coke. But in each case, there was just one symbol sent. You raised your hand with a certain number of fingers raised. So we're starting to see the difference between a symbol and the amount of data that a symbol can represent. Now, in the electronic world that we're living in, how can we vary the characteristics of a transmitted carrier or RF signal to represent different numbers of fingers, if you will? Well, phase shifts, tones sent, discrete levels. These are all ways that we can vary a radio signal to indicate that something changed. And if we can associate a different number of bits with each one of those changes, we can send many more bits than we are sending symbols. And the FCC has a lot to say about a maximum symbol rate. In fact, there are some cases with PACTOR where there's actually a superior form of PACTOR that takes up the same amount of bandwidth, many more bits per second, but because it's a higher baud rate than is allowed on HF, hams can't use it on HF. So the FCC sets those maximums for us. Now, this is getting a little bit closer to the real world that we're all in. And nobody has to really understand this, but if you've been exposed to binary counting, this might help tie some things together. So here what we've done, we've assigned values to each finger. Each is a power of 2, so 1, 2, 4, 8, 16. So in decimal, if we held up all 5 fingers, if you added up all of these numbers, you'd come out with 31. But 2 to the 5th is 32. So how come we've got 31 with all 5 fingers up? Well, the 0 counts as well. So the 32 bits that you can have with 5 fingers is including the 0. So in this case, a symbol rate of 1 per second, let's say, baud, could be a bit rate of 32 bits per second. And our digital modes depend upon this mechanism. They don't use waving hands, of course, but this is the way that they can send a much higher bit rate than what the symbol rate is. So don't worry about understanding that if it was totally new to you, but some of you can relate to it. Here's another chart that sort of shows the same thing in a different way. Here we've got 30 symbols, or 300 symbols per second, but if we can send that as 2 states, on and off, that would be a bit per second rate of 300. If we can multiply those states, we multiply the bits per second accordingly. More definitions. Duty cycle can become very important, and the reason for that is that a lot of our digital modes are 100% duty cycle. That means when you're transmitting, the transmitter never goes off. Radio teletype is that way. It switches between the mark and space tones, but those tones are going out continuously while you're transmitting. So that's 100% duty cycle. If your transmitter is rated at 100 watts, it's probably not rated to send 100 watts continuously. So a lot of people will find that their radios are overheating if they're keeping the transmitter on too much, and will back the transmit power down to about half. Some manufacturers, my ICOM, for example, I can run 100% duty cycle and it never even gets warm. And they didn't pay me to say that, by the way. Now, what is protocol? Protocol are the rules that control the method used to exchange data. How do we chop things up? What are the error codes? Start bit, stop bit. How do we detect errors? All of that stuff is embedded in what's called the protocol. And then the mode is a combination of a protocol with a modulation method. So radio teletype as a mode is normally sent with lower sideband and frequency shift keying. There's another example. Well, RTTY I mentioned in PSK 31, which we haven't gotten into yet. So just some concepts there will help make some of what's to come make more sense, I hope. Okay, so we've seen this already. Just a little bit of expansion. And the methods of modulation are chosen by convention. That means that everybody that does radio teletype will be doing frequency shift keying and using the mark and space tones that most people use. The software for any mode that you're using usually has a number of settings so that you can change some of those parameters. But most hams stick to one particular standard, and we'll talk about that too. Here's another one, FT8. FT8 is 8-tone frequency shift keying sent via USB. So if you're doing FT8 on any band, this is what you're doing. Dig a little bit deeper into frequency shift keying. And here it's in the context of some pull questions. So two separate frequencies of an FSK signal are called mark and space. And the most common frequency shift between the mark signal and the space signal is 170 hertz. There have been some other ones used over time, but this is what the vast majority of people are doing now. And the software that you use to run this mode will normally have settings to adjust these numbers should you have a reason to do so. So here's some pictures. Now what we've talked about so far is direct FSK. That's where we're actually sending ones and zeros to the transceiver, and that's shifting the transmitter oscillator frequency. There's another way of doing it too. Well, first of all, if you're doing that, it's kind of like you're grabbing the big knob on your radio while you're transmitting and rocking it back and forth 170 hertz. Well, that's being done electronically. But the fact is that you're hearing tones on the receive end. Now, audio frequency shift keying, that actually generates audio tones in your sound card software and applies them to your microphone jack. So you're sending the 2000 hertz tones plus or minus 170 actually to your microphone jack or a connector that does the same thing on the back of your radio, and then that's transmitted via single sideband. So FSK generation, okay, we talked about frequency of the transmitter's VFO is controlled directly by a data signal from the computer. That's ones and zeros. Audio frequency shift keying, the audio tones are used to modulate an SSB or FM transmitter through the microphone input. Now, if you actually connected to the microphone input, the audio has to be kept free of noise. Your microphone element shouldn't be picking up noise or TV sounds or whatever happened to be in your room. And then one other tip that we'll expand on, ALC, that stands for automatic level control and compression, must not be used. Now, ALC and compression would be used in single sideband, most likely, but with digital modes, if these elements are active, they'll cause distortion to the digital signals we're trying to send, make decoding difficult on the other side.
And you may have it in an upcoming slide, but the two modes are compatible. So if you're sending AFSK, at the opposite end they can receive, and if they're sending FSK, you can receive. It's all good.
Yep, it sounds exactly the same on the receiving end if it's set up correctly. And Gary reminded me of a controversy in amateur radio. I'm sure none of you can believe that we have controversies in amateur radio. You have 5 hams in a room, they'll all have different opinions. But some people claim that FSK is more pure. But the truth of the matter is AFSK properly set up and adjusted, you can't tell the difference between the two. So people can argue if they want, but there's advantages and disadvantages to each. The direct FSK is something that's pretty much only used with teletype. We have to use audio frequency shift keying for most of the other modes. So that's one of the reasons we're introducing it. So digging a little bit further, radio teletype uses the Baudot code. Another ham controversy is how do you pronounce that? Well, I use Baudot. You can use whatever you want. So it represents or encodes each text character as a sequence of 5 bits. There's one pool question where the number 5 is going to be real useful to remember. That's why I've made it blue. Now to start off the sequence, you have what's called a start bit to start the sequence, and then an inner character pause, which is also called a stop bit, to synchronize the transmitting and receiving stations. So if I'm sitting on my end, you don't know when I'm going to press the A key. So the software has to be ready as soon as I press the A key to send a start bit, and then the letter A, and then the stop bit saying that I'm finished with the letter A. So here's a picture of a paper tape representation, or a picture of the way this code works. You'll notice we've got the letters A through Z, a carriage return, a line feed, a letters command, a figures command, and a space. Now the interesting thing is with 5 bits, 2 to the 5th is 32. So we've got 26 characters in the English alphabet, so we wouldn't have enough to do all of the characters, uppercase and lowercase, plus numbers and symbols. So they do something very tricky. Well, first of all, everything sent in radio teletype is all caps. And if you want to send any of these other things, you would send this code here, figures. So if you send the figures code, which is 11011, see we got the code elements here, 1, 2, 3, 4, 5. So if we were to send a 11011, that would command the receiving system to interpret everything that comes as being a part of this character set. And when we're done sending our numbers or whatever it is we're wanting to do, we would then send the letters code, and we go back to sending and decoding letters. These little dots going down the middle are sprocket holes for pulling the tape through. And then these black marks are like the hanging Chad issue we had in Florida, the past election. These are actually holes punched in the paper. Where there isn't a hole, that represents a 0, 1s and 0s. Oh, I've highlighted 5 bits again for some crazy reason. Baudot uses 5 bits for encoding data, capable of 32 different characters. We talked about not having enough for everything we want to send. And I showed you the letters and figures codes to switch between the character sets. And here's a picture of some of the tape. The Hamfest that I referenced earlier they actually had a machine where you could type a message, it would spit out a paper tape, and then you could feed it into a machine and have that sent. It's pretty cool. So just to reiterate what we talked about, the picture again. Now there's several different speeds that are used with radio teletype, but the most common one that the hams use are 60, which corresponds to about 45 words per minute. Most people can't type any faster than that, or if they can, they'll slow down so they don't overrun their machine. But there are other speeds that can be set in the software. Just have to make sure that the transmitting and receiving sides make the same adjustment. So most radio teletype conversations on HF are at 45 baud, and the most common shift between mark and space is 170. I might have implied that was just the law when I mentioned it before. These are both adjustable parameters, but this is what just about everybody uses. And they have to match on both ends, just like our duck quacking we showed you at the beginning. Now Dave Kassler did something kind of nice with this is a diagram that was in our book, and he kind of goes through and it makes this whole thing a little bit easier to understand with all of the additions. So this is the mark frequency, 2125, space 2295. So those twin spikes we saw on the spectrum display were at these frequencies. We start out with a rest condition when nothing is happening. The mark tone is sent continuously. When we're ready to send a letter, in this case we're going to send the letter D, we're going to send the start bit. So we're going to go from the mark tone to the space tone for a specific period of time, and that tells the computer on the other end, hey, start paying attention. This is the start bit. You have to interpret the next the next 5 time slots that appear here as ones or zeros. So we're going to shift from going from the start bit, we're going to go up, and it knows in this time space, if we've got a mark, that's the number 1. Go back down, we've got a 0. We've got 1, 0, 0, 1, 0. Bits 0 through 4, but that's 5 if you add them all up. That happens to be the code for the letter D. When we're done with those 5 bits, we switch back to the mark, and mark will be longer. It's at least 1.5 times longer than one of these spaces that allows it to be interpreted as the stop bit. And then the next character can start if there's another one. So time is marching on this way. We've seen the mark and space tones, the start bit, the stop bit, and we've repeated the most common numbers that are used by hams. So here, let's see if I told you the truth here. So is the letter D actually 10010? Well, let's look at it. Here's D, 10010. Well, look at that. I wonder how I knew that. Now we're going to move on to phase shift keying. Phase shift keying, we've talked about frequency shift keying where we're actually shifting tones between 2 different values, but that's not the only way that we can manipulate a carrier or a radio signal to signify that a change is going on. So PSK, phase shift keying, rather than changing tones, the phase of one tone is shifted. There's 2 flavors that we're going to be touching on, something called binary phase shift keying and quadrature phase shift keying. And these are the modes used in amateur radio. PSK, by the way, when it came out, it took the ham radio community by storm. It was extremely popular because people could talk keyboard to keyboard for the first time using inexpensive sound card software. So just a little bit of history there. Then when FT8 came along, largely replaced a lot of the traffic that was going on with PSK 31. although FT8 you can't carry on conversations in. Get into more differences as we go. The suffix indicates the approximate baud. It's actually, I think, 31.25 or some silly thing, but it goes by PSK 31. There are variations of this. There's PSK 63, and there's other numbers that are faster versions of the same thing, just clocked faster. But for the purpose of our pool, we'll only be considering the basic ones. Oh yeah, here it is, 31.25 baud. So something to pay attention to. PSK uses a variable length code called Varycode. What that means is that the most commonly used letters in the English alphabet have fewer, they're shorter codes that are sent. For example, the letter E is used all the time, and that gets a very short code in Varycode. Assigns short codes to common characters and longer ones for the less common characters. So the number of data bits sent in a single PSK 31 character will vary between the characters. And here's a key here. Uppercase letters use a longer Varycode bit sequence and thus slow down the transmission. So if your keyboard is locked in caps lock, you want to take caps lock off because you'll be able to send faster Varycode. Now here's something that I've shown to a lot of our amateur extras that they've never seen this, but I wanted to include this because it illustrates what we mean by Varycode. Now this is a Varycode from 1844, and it's Morse code. So that goes way, way back. We didn't have radios then, but we had telegraph. So how does this work? So we'll start here, and if we want to send the letter E, that's a single dot. If we want to send the letter T, that's a single dash. If we want to send the letter I, start here, that's a dot, dot. So the entire Morse code, at least in terms of letters, is all represented. Now let's go way out to the end here. Like here's a J way out at the end. So that's dot, dash, dash, dash. Or we'd say da, 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 da if we were describing it to somebody else that was a ham. So this is just a really, really interesting comparison to the Varycode that we have in PSK 31, illustrating how different characters, the more frequently used characters, can be sent with a shorter code. And another historical bit of trivia, how did Morse come up with this? Well, they looked at a type case at a printer. At a printer back in those days, the type case was a box with a big box with a lot of smaller boxes in it. I used to have a picture, I don't have it now. But and the biggest box would be the box that had the E's. And they'd actually pull the letters out of these boxes and put them into a metal strip to form words. But that's how they came up with this. Well, going to the printers, what is the biggest box? The biggest box was E. So they used the shortest code for that. Printer's type case. Going into BPSK. Now you'll see three terms that we're going to be using here, and they all mean the same thing. In this context, at least, binary phase shift keying means that we've got a single tone, and we're going to send it either in one phase or a different phase. And let's look at this picture here. So we're starting off with a tone, and it's in this phase. It's starting out from the 0 point going high. Now, if we want to change, if we're wanting to send a binary digit, when we make this change here, what we're doing is reversing the phase. It was starting out with a positive going sine wave. Now, right here, we've abruptly changed it to a negative going sine wave. And that's what we mean by a phase shift. So what we're doing here is shifting between, we're shifting 180 degrees. If it senses that shift, then it interprets those as ones and zeros, depending upon how long it stays there or how soon it switches. Now the next leap beyond that is called quadrature phase shift keying, QPSK 31. And here you'll notice, well, I'll just say this first. Important to remember, quadrature PSK modulation in which digital data is transmitted using 0, 90, 180, and 270 degree phase shifts to represent pairs of bits. So not only do we have 4 different points to pick from, but each one of those represents 2 bits. Remember, like the hand and the fingers? Well, these shifts, like for instance, if we switch to a 90 degrees phase shift, that might be 1, 0. This might be 0, 1. So we're actually sending 2 bits for each change in phase. And the picture might help. We're showing 4 different kinds of phase shift. We're going up, and then immediately we're going to bounce down and reverse the phase. Or we're going to change it at a different state. It's kind of hard to see on the diagram, but some of these happen at 90 degrees. Like this one would be 90, it's near the top. The 0 would be here in the middle. And this one is switching, looks like 270. And here we've got some 180 degree shifts. So you're seeing that these are happening, they're interrupting the sine wave, or they're changing its phase at these possible points. Now, quite often when we see 3 things together like this, there's an all of these answer coming up in the pool question. Now, QPSK uses 2 tones. Guess that wasn't mentioned up here, but that's the fact. It's using 2 tones. Because it's using 2 tones, it's sideband sensitive. Remember that AM signal we saw way back in the beginning, where a lower frequency tone is in a different place on upper sideband and lower sideband, relative to each other, a lower and a higher tone. So because 2 tones are used here, that makes QPSK 31 sideband sensitive. A big improvement here, with all of this extra stuff that's going on, its encoding can provide some error correction. So by sending those bits in a certain way, we can detect certain kinds of errors and actually correct them in the protocol. And what's also something that's cool is its bandwidth is approximately the same as BPSK 31. So the baud is the same, but we're changing, or the symbols per second is the same. Symbols per second and baud are the same because we've got more things to pick from and we're using multiple bits for each shift. We can get a much higher throughput and some more features. So that's the concept of QPSK. Now I've shared some sounds. I hope these work. If you're tuning around on the radio, you might hear some of these things. I've used these 3 because they're fairly common. I used this one, MFSK 16, because I like the way it sounds. There aren't too many cams using this mode, but it's out there. And then I've got a link here that'll work when you get the PDF from Gary that's got dozens and dozens of modes. So let's just give a quick listen here if it works. I'll see if it works.
Turn off your
I got to
spotlight
turn off
first,
the.
and while you're doing that, I just mentioned for those in the Zoom classroom, Zoom has its filters, and it may try to modify the sound. It doesn't like tones and things appearing in Zoom, but those on YouTube, you'll hear it without any problem.
Okay, and should some of you not, when you get the PDF, if you're interested in this, you can listen tomorrow. So RTTY. See if I can play that. Let's see, is that going out? Was that a yes?
That's done.
Oh, okay, that's done. Okay, JT65. I can't hear it here. I have to depend on Gary to tell me. I gotta close this first. JT65. That's happening. Kill it. Oops, here. PSK 31. Notice this is a very different sound. Oh, okay. I didn't realize that. Kill this one. Then this is the one that I just thought sounded so cool. The first time I heard this on the air, I couldn't believe what I was hearing, but see what you think. Isn't that interesting? And then we couldn't possibly leave this without listening to FT8. These were ARRL files. I couldn't find one that they had for FT8, but this is even better. I'm going to bring up this website, Wiki Sound Library.
We don't see it.
You don't see that. Let me see if I can.
There you go.
Okay. It's this one here. And I'm going to do it Control F for find and do FT8. There it is. And play it.
The arrow on the left.
Yeah. Right. You'll get very used to hearing this one. And let me turn it off. So this just goes on and on and on. We just touch a very few of the modes here in this chapter, but if you're curious about anything else, this website's got them all. And again, all of these links will work for you when you get the PDF. There's one book that I highly recommend. It's from the ARRL. This is also available. You can get it from the ARRL store or Amazon. The ARRL's shipping cost, I think, is like $7.50. If you're an Amazon Prime customer, of course, you can avoid the shipping. And it's also available in a Kindle book. I think these are like $20, and the Kindle book is only 10. If you pursue getting one of these, though, be sure to get the 3rd edition. I've got all 3. The 1st edition was kind of that's interesting. 2nd edition was a little better, and the 3rd edition they finally got right. So most of the modes that we talk about in this class are discussed in this book. It's not a tremendously long book, but it will give you some pointers in getting on the air with some of these modes. So it's something I recommend if you're interested. Some questions. Which of the following describes the Baudot code?
Charlie. D.
Charlie.
Charlie, yep. That was the number 5 I kept urging you to remember. What's the most common frequency shift?
Bravo.
Bravo.
107.
Bravo, correct. Which type of code is used for sending characters in a PSK 31 signal?
Nope.
Yeah, that was our friend the Varycode. Which of the following statements is true about PSK 31? I love some of these wrong answers.
Bravo is true.
Bravo.
Bravo, right. Use longer Varycode symbols for uppercase letters, which slow things down. What is QPSK modulation? A lot of words to read there.
D. Delta.
Delta.
That was the one using the 4 phase shift options or possibilities. Modulation, in which digital data is transmitted using 0, 90, 180, 270 degree phase shift to represent pairs of bits. Which of the following is a characteristic of QPSK 31? Read carefully.
Alpha.
All
All
choices
these
D.
choices.
Yep. Now, I did notice something in going through this material. That this was a revision, of course, from the previous pool. The pool committee actually missed a couple of these. They changed all of the above to all these choices are correct. So if you see an all of the above answer, that means all these choices are correct. I don't think that would confuse anybody, but there are a couple of questions that come up that way. All right. Now, it's probably a really good time for a break here. We're 5 minutes early, but I've kept you late for breaks before, so I hope I'll make up for that. So let's take 5 minutes and stretch, get up, get a drink of water, pet the dog, whatever you'd like. We'll be back in 5. we're back. We're going to jump into the second part here. A lot of the content was wrapped up in definitions and so forth, so I think the second half will go a little bit quicker. I saw in the comments here that somebody asked about what some of the software programs were that would enable these modes, and somebody answered.
That was me.
Oh, that was you, FLDigi and WSJT for FT8. And if anybody's a ham radio deluxe user, they have a suite of programs called DM70. I think that's what it is, or 700, and it does basically all the digital modes except the WSJTX modes. So those are three that you can use. All right, packet basics. All right, this refers to transmission of data in structured groups. Now here's an example down here at the bottom. These are all individual, probably 8-bit bytes of data in all of these little boxes. And a packet normally has a header, then it has what's called a payload. This is my message for you. And then a checksum. It's more complicated than this, but this is the high-level concept of what's going on. There is one pull question that asks about what is contained in the header. The start of the packet will contain control, routing, and handling information. In other words, where's this packet supposed to go and how are you supposed to handle it? Synchronization and error detection. So these are called structured groups. Again, just some more background. And here we're showing the header, the data, and the trailer. The data is what we're actually wanting to send to the other person, often with compression. The trailer, additional control and redundant information used for error correction in the trailer. And then a term that you'll hear is CRC, or the cyclic redundancy check. That's a technology built into several of these modes that allows it to determine if the packet was sent correctly. And it's based on a calculation of the content of the overall packet. Forward error correction. Now the concept of forward error correction is we're going to send extra data inside the packet that will allow us to compare data earlier in the packet and then determine if it was correct or not. And extremely simple, and I don't know if anybody actually uses this method, but let's say that you were to send the data or certain parts of the data 3 times. Now you'd be able to vote 2 out of 3 and make a choice, make a decision on the one that it probably should be. So that would be one algorithm for data correction. It's called forward error correction because it's sent along with the data. The correction information is there and can be decoded and used. So that's forward error correction. There's also a concept that I would call reverse error correction. And that idea is if a packet is received and it's not received correctly due to a CRC error, for example, or they couldn't put it back together, then it would send what's called a NAC, which is not acknowledged. So we've got forward error correction running up here. It assumes that you're gonna get what was sent. And then in an automatic repeat request mode, a NAC, not acknowledged, will be a response to a transmitted packet, and that will cause the request for retransmission of that packet. I've got a diagram of how that works coming up, which is right here. Automatic repeat request. So we've got a sender and a receiver. So transmitted data, received data. So we're going to send data to a receiver, and it says, it's okay, happiness. So it's going to send an ACK back to the sender. The sender is going to say, okay, got that one. I can go ahead and proceed with the next one. These are entire packets that are being sent. So another packet of data will be transmitted to the receiver. Uh-oh, not okay. So what do you suppose happens? He'll send a NAC, automatic repeat request, a NAC, not acknowledged. So the sender will say, I'm going to have to resend that one. And that's what happens. Data is resent. is received okay, and then it's acknowledged. So that sequence of packets has now gone through. Everybody's happy, and we fixed the problem that occurred in the process. Now notice that this only works in the context of one sender and one receiver. Because if you had one sender and many receivers, one receiver, one receiving station might have received it okay, the next one might not have. So all of these signals that would be coming back to the center would be a horrible confusion. Because some are saying, yeah, I got it. Others are saying, no, I didn't get it. And it just doesn't work. Now PACTOR, and this is a pool question, is an ARQ, automatic repeat request protocol. Therefore, joining an existing contact is not possible. PACTOR connections are limited to 2 stations. And generically, that would be true of any ARQ protocol. Winlink, fascinating system. I've got some facts that we'll share in a couple slides, and then I'll have a system diagram, excuse me, that I think will tie some of this together. So Winlink is an infrastructure. Note that word. It's not a mode or a protocol. It's an infrastructure for connecting amateur stations to remote message servers, RMSs they're called, and international common message servers via the internet. Well, this is sounding interesting already. Now, another name for a remote message server is a gateway. The concept there is a transmitting station, such as you, would be sending to a remote message server, which, if it's connected to the internet, would be a gateway station for you. Winlink, continuing on. Oh, we got 3 things in a row. What do you suppose is coming? An amateur radio. What is Winlink? It's an amateur radio wireless network to send and receive email on the internet. Is that cool or what? It's a form of packet radio. And it's a wireless network capable of both VHF and HF band operation. Now, remember I said Winlink was an infrastructure? Well, that infrastructure we need to talk to it. So that requires a hardware or software modem to connect the radio to the Winlink infrastructure. PACTOR uses a hardware modem. VARA, which is relatively new over the past couple of years, is a software modem, sound card modem, if you will. And there's a question that says, what is VARA? Well, VARA is a digital protocol used with Winlink. It's a program that you download and put on your computer. Winlink Express is probably the most popular client for Winlink. So in terms of what software would I need to obtain to use this, I believe these are both free. VARA has a free license, and then they have a paid license. I think it's about $60 that brings the VARA throughput all the way up to what PACTOR can do. And that's what most of the emergency, like RACES and so forth, are using emergency operations in ham radio, VARA and Winlink. Winlink, I know, is free. And this is the solution most amateurs are using right now, Winlink Express plus VARA. And VARA is available in a couple of flavors. There's VARA HF, there's VARA FM, and then there's kind of an accessory program called VARAC, which is a chat program. And that works just like you can imagine. It's for sending chat messages between hams. So here's the diagram that I promised. It might be a little bit hard to read, but here we've got individual amateur stations. The radio is hiding behind the computer. I guess you can't see it, unless we're wireless between the computer and the tower. No, that was a joke. So they go using the software that I talked about, PACTOR or VARA HF or VARA FM. They go out to the remote message servers, which are interconnected to the internet, and then those go out to common message servers, CMS, that are located all around the world. These actually reside in the Amazon cloud, I found out. I think they still have these other stations that consolidate the data and store it. So what happens here, if you want to send an email message, you compose it with your Winlink Express and then send it up to the system. If somebody else logs on and wants to check their email, they go up and look for it, and it comes down. Now, one of the beauties of the system is that if any piece is broken, the other pieces can backfill and still get the message through. So portions of the internet can be down, the entire internet can be down, then of course they're depending upon these to route that traffic and store it and forward it. It's also possible using a telnet session to bypass the radio and go directly into the system. A little bit more information on winlink.org. Extensively used by amateur emergency services. The Puerto Rico disaster we had a few years ago, they were begging for hams to show up with packet-enabled systems. It has non-ham uses as well. Maritime, for example. The infrastructure is completely run by hams, and you can transmit messages and files via the interlink. The interlink. How about the internet?
Interwebs.
Yes. So we're going to move on to something new, WSJT modes. Here we've got a little robot here. So this is a whole suite of modes. When you go to their website, if you Google on WSJTX download, you'll go to the site. It includes all of these things. Not all of the programs within the suite will be of interest to you, but several of them will. Capable of commuting at extremely low signal levels. It can operate 30 dB below the noise level, which is like 1,000 times less power than noise, which is amazing. You won't be able to see or hear the signal, and the WSJTX software will be able to, with one of these programs, be able to transmit and receive those messages. It was originally developed for moon bounce. In a little fact here, the moon is, well, it's kind of on an orbit that changes distance, but call it 238,900 miles away. Okay, so you've got to go all the way to the moon, but there's a little problem in communicating via the moon, and that's that there aren't any hams there. So the signal's got to get to the moon and then come another 239,000 miles back if you're going to make a contact. There's a lot of amateurs that are doing this, by the way. I haven't, but I think it's pretty interesting. Now consider that the Earth's circumference is only about 25,000 miles. So look at how much further the moon is away. So you might think talking from the United States to Australia is quite a feat, but which is pretty much on the opposite side of the world from us. The moon is really an amazing feat. The way they had to do this before the WSJT modes was just amazing. Huge dishes and super cooled preamplifiers and as much power as you could put out. This has made it possible for the average ham as long as you can get an antenna up. So it was released in 2017, June 29th. I think I stumbled onto it in August of 2017. And at the time I was living in a HOA, had very limited antennas. And so just about all of my contacts were FT8 back then, because nothing else would work. And I think over the next year or two, I accumulated about 5,000 contacts on FT8, including worked all states as far as awards and DXCC, 100 confirmed countries. So that kind of got me started in ham radio once I became active again. So it was written by Steve Franke, who's passed away now, Joe Taylor, K1JT. Very narrow bandwidth. You'll see 45, 47, 50. That's rounded off to 50 here. And it's 8 tones spaced very close together, 6 hertz. And this is a frequency shift keying mode. And it takes 15 seconds to transmit, and then you're quiet and you listen for 15 seconds for a reply, and then the cycle repeats. 8 frequency, 8 FSK mode. This is funny. FT8 has been controversial amongst hams. Some people love it, like if you're in a place where nothing else will work, like I was, and some people hate it. They say, well, this isn't real ham radio. It's taking away people's interest in CW. It's the worst thing in the world. Well, it sure is a lot easier to work DX. So look at some of these levels, the noise ratios. So single sideband, you need about 10 dB above the noise for a good conversation. Very readable. CW, minus 15, much, much lower. And then these WSJT modes are way, way down. So if you look at FT8 at minus 21, in single sideband, which is plus 10, that's a difference of 30 dB. So 1 watt of FT8 is equivalent to about 1,000 watts of single sideband. Now take that in for a minute. That's incredible. It's really incredible. That's why you can work stations all over the world that you can't even hear, and you can get to things like worked all states and worked all continents, DXCC, in a reasonable period of time using digital. Just by comparison, 1 watt of CW is worth about 300 watts of single sideband. So CW used to be the very best way you could do it. But now if you're interested in those really weak signals, FT8 and its cousins are even better. Look at Whisper, that's way down at minus 31. We'll talk about that more. Now here are some stats that were released by Clublog, and this goes back to when FT8 was first released. And what it's showing is the signals that it was seeing on the bands. Within just a couple of months, it became based on the number of contacts being made by hams, it went from nothing. So we've got CW, phone, RTTY, PSK, all of these other modes, and FT8 just outstripped them. It was extremely popular, a little bit like PSK when it first came out, when it was the best thing on the block. So FT8 took the ham world by storm. Here's a little bit of math, 15-second exchanges. The effective data rate is only about 5 words per minute, but they're not exchanging very much data. I've got 1, 2, 3 blocks up here, and this represents about all you can do with the information in FT8. It's designed for minimum information to qualify for a contact, definitely not a conversation or rag-chew mode. So characteristic of the FT8 mode, typical exchanges are limited to call signs, grid locators, and signal reports. That's the 1, 2, 3. But it is a valid contact. Takes about 2.5 minutes to complete one. Operation is synchronized. You transmit for 15 seconds. You receive for 15 seconds. So you've got the start times of 0, 15, 30, and 45 seconds during each minute. These are called the odd and even slots. So 0 and 30 are even, 15 and 45 are called the odd slots. Now a requirement when using FT8, computer time needs to be accurate within approximately 1 second. I've seen decodes out as far as 2.5 seconds, but that's not reliable. You need software on your computer that will make sure that your computer clock is locked to within 1 second of UTC. All right, FT8 is an AFSK mode, audio frequency shift keying. So our sound card, the software in our computer is generating the tones being fed to your transmitter microphone input electronics. The pool wants us to know that a type of modulation, the type of modulation used by FT8 is 8-tone frequency shift keying. Which of the following narrowband signal modes can receive signals with very low signal-to-noise ratio? Well, you know what, that's FT8. That's how it'll appear as a pool question. Now, the signal reports are kind of confusing, even if you think you understand them. A signal report of +3 means a signal-to-noise ratio that is equivalent to plus 3 dB in a 2.5 kilohertz bandwidth. Well, if you can kind of recognize these words, you'll get the pool question right, but just to explain it, a small amount of what that means, a single sideband channel is approximately 2.5 kilohertz, and the noise that you're going to receive is a function of the amount of bandwidth that you're listening to. So if you were listening to a very narrow bandwidth, the noise would be less than if you were listening to a wider bandwidth. So what FT8 does is it compares this bandwidth to the signal level, signal-to-noise ratio for the FT8 signal itself. So a simple way that I like to think of it is that we're seeing a signal that's 3 dB above the noise. And you don't have to get into all of this other gobbledygook unless that interests you. So typical signals will go down to about minus 24. And maximum signals, I've seen them up as high as 20. Here's our friend, this diagram again. There will be a pool question that asks, where do you look for FT8 on 20 meters? Now notice the answer that they give you. It's 14.074 to 14.077. Now since it's upper sideband, if your radio was indicating 14.074, if you add 3 to that, that would be 14.077. That's where they get this number. So it's basically someplace in that single sideband channel. So the hint again, 074, the same trick we used previously. Now how do you choose an FT8 transmitting frequency? I'd say the most confusing question in the new pool was this one here. And this is what it says. A good practice when answering a CQ, find a clear frequency during the alternate time slot of the calling station. Well, the problem with that is you've got to understand a whole bunch of stuff about FT8 to make those words actually make some sense. I'll go through a generic thing and then come back to this one again. So choosing an FT8 transmit frequency, and again, I've made thousands of these, so this is from experience and what other people have written. In general, find an open spot on the waterfall and lock your transmit frequency there. So here we've got some signals on the waterfall. These are all about 50 hertz wide, starting 14.074. Should be over here, and then 14.074 to 14.077, that 077 would be up here. So these little 50 hertz blocks are different signals that are transmitting. So I say find an open spot on the waterfall and lock your transmitter. Okay, so here's a spot. So how do we lock our transmitter? So place and hold the cursor over an open slot, would be here, and you hold the if you're using your mouse, you hold it there, and then do a shift click to move the red goalpost. Well, some people call these things goalposts. The little red symbol, which you can barely see, is your transmit frequency, and the little green one right below it is your receive frequency. You only have to worry about moving your transmit frequency. So hold the cursor over an open spot, shift click to move the red goalpost, which is your transmit frequency. And then make sure in your settings here, there's a setting, impossible to read, but it says hold TX frequency. You want that to be checked. That way your transmit frequency will stay there for not only this QSO, but any other QSOs that you make. So check hold TX frequency box and leave it there unless conditions change. If a whole bunch of people start jumping on where you're wanting to transmit, you just find another clear spot and select it. So now let's see if we can make some sense out of this. When answering a CQ, find a clear frequency. Okay, we understand that, because if you're transmitting right over somebody else, it might be difficult for that rare DX to decode you. Find a clear frequency during the, now this is the part that's kind of, remember we're transmitting for 15 seconds and receiving for 15 seconds? So that's what this is referencing. Find a clear frequency during the alternate time slot to the calling station. Well, I don't, and I don't know anybody else that watches for time slots in between transmit and receive it, and then pick one of those. The common practice is just to find one that's clear of everything, and then go ahead and try to make your contact.
And I just wanted to point out that the screens you're looking at here are part of the WSJTX software.
Yes.
So even if your radio doesn't have a waterfall display, what we're seeing on the top there, the software does. And so you will see this very display.
Yes, thank you for that. This has many aspects. It's a very deep subject, so I don't claim to know more than probably 70% of it, and I've been doing it for quite a while. Okay, so we dealt with the most complicated question in the pool. So some operating tips. Now here we've got a picture of a confused chicken. And here we've got that diagram that we showed earlier of the way FT8 is just taken over the world in terms of the number of QSOs that are happening in ham radio. So here's some random things. They're pretty much all in black, but some things I'll share with my ham friends. You never want to transmit on a DX station's frequency. That's an absolute no-no, because other people will, and then it'll just be a mess. As conditions change, move your transmit frequency to stay in the clear, if possible. If a needed DX is not answering you, try moving your transmit frequency to another clear spot, because the spot you're transmitting on may not be clear in Africa. When answering, and they talk about, do you want to be on the even slot or the odd slot? Well, when answering a CQ, the TX even 1 box that was on that setting screen I showed you earlier, the operating screen, if you're answering a CQ, then the software will know what that person is sending, and it will automatically put you in the correct slot. So you don't have to do anything. All you have to do is double click on his CQ signal, and your software will know which slot to use. Now, when you're sending a CQ, you can pick the time slot for your transmission. And there's kind of a convention. European stations tend to be transmitting on the even, I believe. I might have this backwards, but the recommendation is that other stations trying to call them be on the odd slot. Now, don't expect you to remember all of this, but I would like to introduce you to the most awesomest, I made that word up, the most awesomest guide to operating FT8 on the planet. It's a pretty big statement. Go to this website here. Gary Hinson has written a marvelous document that's really accessible, meaning it's easy to understand even if you're new to this, that really gets into a lot of this detail. And this link will work for you. Now we'll move to whisper. We see some boys whispering. WSPR is pronounced whisper. Weak signal propagation reporter probes the potential propagation using low power. So you can be sending out whisper packets, and then you can go out to a link here and see where those packets were received all over the world. So it also sends minimum information, power level, call sign, and grid locator. In listening stations in Africa or Europe, if they heard you, their software will be set to send that to WhisperNet. And you can go into WhisperNet and see where you were heard, which is really handy. Now, a common usage is to provide propagation data on the really low frequency bands, 2200 and 630 meters. That's where a lot of whisper activity is. And their thought is, well, we're just going to transmit and see how far we can go. It's excellent for comparing antennas. So I'm working on getting a hex beam up, and I'm currently using end-fed wire antennas. And I'm going to try sending whisper for 5 minutes on one, and then 5 minutes on the other, going to WhisperNet and seeing the difference in received signal strength. So a lot of people that play with antennas use whisper for that. One pool question: which digital mode is used as a low power beacon for assessing HF propagation? That's our friend whisper. All right, well, this was kind of new to me. It's been around for a while, but it's now, there's a couple of pool questions, so I had to understand it a little bit. So the idea is amateurs share some of the wireless frequencies, 5 gigahertz, 3 gigahertz, or 5 and 2, I guess, are what we're most used to, but this is available as well. And it can use 900 megahertz, 2, 3, and 5 gigahertz amateur bands. And it operates by using standard Wi-Fi routers with special software. Certain routers are capable of being used that way. Now the routers, your typical internet router in your house is 100 to 200 milliwatts. Hams on the 2.4 gigahertz band are licensed to go as far as 100 watts. So we can cover an entire community, a town, a special event, or disaster area.
10 watts, I think. for
10,
spread.
is it 10? That's right, because this is spread spectrum. Even if the limit is 100 on 2.4 for spread spectrum, yeah, I think you're right. Thank you. I will adjust that. But significantly more power than what you can use on your home internet router. One of the features with a mesh network, this is called a mesh network, all these nodes are interconnected with a mesh network, with mesh network microwave nodes. Now by microwave, they're talking things in the gigahertz range. Slipped another word on us. If one node fails, a packet may still reach its target via an alternate node. So that's a feature and a pool question. And the primary purpose of the Amateur Radio Emergency Data Network is to provide high-speed data service during an emergency or community event. So these are the only two things you'll need to know as we get into the questions. What part of a packet radio frame contains the routing and handling information?
Charlie?
That's the header. How does forward error correction allow the receiver to correct data errors?
Charlie?
We sure like Charlie, don't we? That's correct, by transmitting redundant information with the data. In an ARQ mode, what is meant by a NAC response to a transmitted packet?
Alpha.
Yep, NAC means not acknowledged, so they're requesting retransmission of the packet. How do you join a contact between two stations using the PACTOR protocol?
C.
You don't?
You don't, yep. It ain't gonna happen. Joining an existing contact is not possible. PACTOR connections are limited to two stations. Which of the following describes Winlink?
Delta.
Alpha.
Alpha is correct, but beta is correct, and Charlie is correct, so it's all of the above. And here's one of those cases where the pool committee still has it as all of the above, but all of these that means the same thing. Because when you take your test, this might be up here somewhere in the middle. What is another name for a Winlink remote message server?
Bravo.
Bravo, that's the gateway. What is VARA?
Bravo.
Digital protocol used with Winlink. That's basically the modem software that's running on your computer to interface with the Winlink infrastructure. Which of the following is required when using FT8?
Bravo.
Bravo.
Bravo again, computer time accurate to within approximately 1 second. And what type of modulation is used by FT8?
Alpha.
Alpha.
Alpha 8-tone frequency shift keying. Which of the following narrow band digital modes can receive signals with a very low signal to noise ratio? I don't think we talked
Bravo.
about this, but I think it's obvious. Did I hear Bravo? Yeah, FT8. These are other things that are real or used to be real, but FT8 is the correct answer. What does an FT8 signal report of +3 mean? crazy.
Charlie.
Yeah, it is Charlie. Signal to noise ratio equivalent to plus 3 dB in a 2.5 kilohertz bandwidth. A bunch of techie words. What crazy. Some of these distractor answers are really crazy. But if you didn't have a clue, I guess they could get you. Which of the following is a common location for FT8?
Charlie.
Winlink.
Yeah, I think there's some words missing out of this. Well, no, because common location, yeah, this is the only one that could possibly be true. I need to check the wording on this one. But Charlie is correct. That's our 074 clue again, second question where that helped us. Which of the following is good practice when choosing a transmitting frequency to answer a station calling CQ using FT8?
Delta.
Yes, finding a clear frequency. And clear frequency, that appears, yes, some of these would be very plausible, but hopefully with the discussion we had, this you'll be able to pick this one out. Which digital mode is used as a low-power beacon for assessing HF propagation?
Alpha.
That's whisper. Yep. Which is true of a mesh network? True of a mesh network microwave nodes.
Bravo.
Bravo. If one node fails, a packet may still reach its target station via an alternate node. What is the primary purpose of an amateur radio emergency data network, mesh network?
Charlie.
Provide high-speed data services during an emergency or community event. Charlie. All right, 2 more sections to breeze through. And we won't, I think we'll have time for our bonus at the end. We'll see. If not, I'll flip through it quickly and then you'll know what it is and you'll have the links tomorrow. General license, okay, section 6.4, receiving and transmitting. Now this is just general information about receiving and transmitting digital modes. So RTTY normally transmits using lower sideband. Everything else, including all of the JT modes, use upper sideband. So you just have to remember these. For me, it's easy to remember the upper sideband here because I've used it a lot. Digital decoding issues. We got 3 things in a row again. Read carefully on the pool question. Digital decoding issues. The mark and space frequencies may be reversed. You may have selected the wrong baud rate, or you may be listening on the wrong sideband. And that's reason that that's an issue is because the relationship of the tones and digital data would be inverted. So that sounds like an all of these answer. Bandwidth of digital modes. Now the FCC defines the rules for bandwidth, just like they do for other signals, and digital modes are regulated accordingly. A higher symbol rate requires wider bandwidth. And I've got an analogy here that may be helpful, which we'll get to. Now by packing more bits into a symbol, the net bit rate can be increased while keeping the symbol rate the same without increasing bandwidth. The bandwidth of a PACTOR3 signal at maximum data rate is 2.3 kilohertz. So again, it's approximately the width of a sideband signal. And I don't think this is a pool question anymore. This might be one I forgot to black out, which I'll fix if that's the case. Now here's my analogy. Here's a pond. The pond is very smooth. And if we tap it with our finger, or put some water drops, we're going to get these waves spreading out from the pond. So the more you disturb the pond, analogous to an RF carrier, the greater the waves or the bandwidth. So if we tap the water faster, we're going to make more waves. If we tap it harder, we're going to make more waves. Anything that we do that will disturb the Ethernet, if you want to call it that, anything that we do to disturb the purity of the signal that we're trying to transmit will cause it to consume more bandwidth. Some examples. A higher symbol rate, we've already talked about. With CW, as you speed up the CW speed, that increases bandwidth very slightly. In an FM system, the FM deviation, the wider that is, the more bandwidth. The harder you modulate a single sideband signal, the more space it's going to take. And then some digital modes tend to disrupt, if they do their phase crossings at places other than 0, they will cause greater bandwidth. So a lot of the digital modes have got very special techniques built into them to keep those as smooth as possible. So the more you disturb the water, the more bandwidth you're going to need. So here's some bandwidths of the various digital modes. When more is gone, that's VARA now. FT8, 50 hertz. Whisper, 6 hertz. Really, really narrow. So with FT8, if we've got 3 kilohertz to stuff it in, that's dozens of contacts that can be going on in the space of one sideband channel. So if you hear hams telling you that FT8 is going to consume the entire ham bands, well, no, not true. Might be taking up 1 or 2 sideband slots at most. And more than one only if the primary one just gets completely jammed. Just general information here. PSK 31 and FT8 are about the same. Now we'll get to duty cycle. This symbol down here, what this means is my radio is too young to smoke. All right, so some modes have high duty cycles that could exceed the transmitter's average power rating. Most amateur equipment is rated for ICAS, which is Intermittent Commercial Amateur Service, meaning that if it's a 100-watt transceiver, it's not intended to be running 100 watts continuously, or it would overheat. CCS, or Continuous Commercial Service, would be a transceiver that's rated for full key down, unlimited time. So a lot of the digital modes have high duty cycles, and you don't want to overheat your transmitter by having it on all the time at 100 watts. So these are all modes that are that way. ARQ modes, because they send a packet and wait for an acknowledgement, it's less than 100%, but it's still very high. So a general rule of thumb that a lot of hams follow is reducing their transmitter power to about 50% of maximum for most digital modes. And of course, with the WSJT mode, since they're so sensitive, that usually won't affect your ability to reach out and talk to people. Signal quality. We all want to put out clean signals. The excess audio levels can cause distortion and splatter, just like they do on sideband. On a waterfall display, vertical lines to each side of the main signal indicate overmodulation. This one appears to be kind of dirty. You just want the center part, not all the stuff on the sides. So you want to keep your data audio level set correctly. Overmodulation cause splatter, spurious emissions. And any distortion in your outbound signal will make the receiving station, they'll have a harder time copying you. And then I've got, remember the movie The Good, Bad, and the Ugly? Well, we've got the digital equivalent here. This is PSK 31. This is pretty good. And this is bad. It's got stuff out here. And this is the ugly. They got very sharply defined vertical lines going way, way out. And a link here with some more information. Now ALC. ALC is automatic level control. ALC is kind of important for sideband transmitters because if you put too much audio on, you recall that if you have no speech coming into a sideband transmitter, you've got no power going out. But if you have maximum speech, you could it could be trying to exceed the 100-watt limit. So what ALC does, automatic level control, if it senses that the transmitter is being driven too hard, it'll back off on the input. It'll actually turn down the microphone gain in terms of a single sideband, and because the audio frequency shift keying modes are actually feeding the transmitter input, ALC, if we're driving that too hard, will back down on the digital signal, making it nonlinear. So ALC is used to prevent excessive drive to the amplifier inputs, transmitter amplifier, power amplifier. Normal ALC action will reduce the transmitted audio level if too high. Since peaks may become compressed, signals can be distorted. Speech, don't really care. With digital, it will hurt you. More sensitive than single sideband. And then the pool question related to this, the AL system should be inactive when transmitting audio frequency shift keying, which includes FT8, because ALC action distorts the signal. So what a lot of hams will do, they'll adjust their digital levels such that they'll be putting out as much transmit power as they care to. They might want to be putting out the full 100 watts, but they'll be watching the ALC meter on their transceiver to be sure that ALC isn't becoming active. And then they'll back the level down so that the ALC is not indicating anything. And most metering on most transceivers will have an ALC rating or range. In this case, there's sort of a bar here, and that bar is where you would want the meter to be for single sideband. Well, for digital, you'd like that to be actually not even indicating ALC. And with a really good transceiver, you might be able to get 100 watts with no ALC action, or turn it down until ALC is indicating 0. So when using digital mode, your ALC system should either be disabled, which I don't think you can do, you might be able to, or the microphone input level and gain turned down to the point where ALC system does not activate. So monitor ALC during transmission. It shouldn't activate. Some transceivers do ALC in kind of a weird manner, and some ALC action would be normal. You have to read your manual. Ellercraft, some of the Ellercraft radios are an exception to what I just said. Questions? And then we got one more section and we're done. Which mode is normally used when sending RTTY signals via AFSK with a single sideband transmitter?
Delta.
Yeah, this is the lower sideband. Okay. This one, which sideband is used for JT65 and the WSJT modes?
Bravo.
Bravo, that's upper sideband. We've covered the possibilities there. What could be wrong if you cannot decode an RTTY or other FSK signal, even though it is apparently tuned in properly? Read carefully.
Delta.
Yeah, that's
Delta.
all of those.
All of the checks.
Yep. What is the relationship between transmitted symbol rate and bandwidth?
Bravo.
Bravo.
Higher symbol rate requires wider bandwidth. Higher symbol rate, we're tapping the surface of the pond faster. Why is it important to know the duty cycle of the mode you are using when transmitting?
Bravo.
Bravo.
Bravo. Some modes have higher duty cycles, have high duty cycles that could exceed the transmitter's average power rating. They'd overheat. Some transceivers actually will give you a temperature reading of the final amplifier, which you can watch too. What is indicated on a waterfall display by one or more vertical lines on either side of a data mode or RTTY signal?
Delta.
Delta.
Overmodulation, exactly. And then why should the AL system be inactive when transmitting audio frequency shift keying data signals?
Bravo.
Bravo.
Well, yeah, I'm sorry, it is Bravo. I was thinking something else. The ALC action distorts the signals. Yep. So forgive me for that mental lapse. And then this section, and then if we have time, we'll go into some more detail on FT8. This is a short section. Digital operating procedures. First of all, we'll talk about Winlink. System gateways are connection points for digital messaging systems. To establish contact with a digital messaging system gateway station, transmit a connect message on the station's published frequency. That's the answer we're looking for. Now, gateways do have published frequencies, and I've got the Winlink RMS channel listing here. Now, I suspect most of you aren't going to be doing Winlink in the early days of your general ham career, but if you like the idea of doing email or emergency communications, maybe you'll get in sooner than I'm thinking. You can also see the Winlink Book of Knowledge link here for that. Note that Winlink gateways will support Pactor and Vara, some more information there. This is the important thing to remember. Now there's three fairly arcane, they seem arcane, I can see that they are important, but they're a little confusing. Miscellaneous FCC rules for digital operations, so 3 pool questions relating to this. Now, automatically controlled stations transmitting RTTY or data may communicate with other automatically controlled stations anywhere in the 6 meter or shorter wavelength bands and in limited segments of the HF band. If you'll just quickly take a look at page 6-15 in your book, there's a table there that gives you the automatic automatically controlled station frequencies. So an automatically controlled station is one where a control operator does not need to be present. It's fully automatic. Maybe think of repeaters is another example. When operating under automatic control, outside the automatic control band segments, the station initiating the contact must be under local or remote control. I had to do some studying on this because it didn't really make much sense to me. So the FCC has specific frequencies in the HF bands on the table that I mentioned, and they kind of expect that's where the communication for automatically controlled stations is going to be. But there are automatically controlled stations in foreign countries that are outside the purview of the FCC. Now, we can talk to those stations if we like, but in that case, we have to have a control operator present. That's how to interpret this one. So when operating under automatic control outside the automatic control band segments for the US, the station initiating the contact must be under local or remote control. Local means you're standing at the transmitter. Remote means you're in control of the transmitter on a hilltop someplace from your station. You have to be present. And then finally, under no circumstances are messages sent via digital modes exempt from Part 97 third-party rules that apply to other modes of communication. So there's nothing special about digital. The same rules apply. And because most of us don't think about automatic control very much, or what are called auxiliary stations, closely related, there is a really nice frequently asked questions listing at the ARRL site that I've put the link in for here. Okay, there's Pactor and Vara interference concerns to talk about. They're tolerant of much interference and fading. Symptoms may result from other signals interfering with Pactor or Vara transmission. 3 in a row here again, should be a clue. Frequent retries or timeouts are an indication that there could be interference. Long pauses in message transmission while the X and X are flying around. Failure to establish a connection between stations could all be due to interference. And if you've got a conversation or a connection that's up and running, when failure to exchange information due to excessive transmission attempts when using an ARQ mode, like Pactor or Vara, occurs, the connection is dropped. So if it tries 15 times in a row and it's not successful, I don't know what the number is, but it'll drop the connection. Now this one here, for some reason, people have a really, really hard time getting this. So I'm going to explain it a little differently here, and I'm hoping we'll get all of the right answers when we get to the pool question. Everybody's seen waterfall displays, either in pictures or on real radios, or on FT8, or web SDRs, whatever. So this is what's important. Frequency is horizontal. So you notice that we're going from 14 megahertz to 14,350. Okay, so frequency is horizontal. I'm going to go down to this one. Time is vertical. So as these signals come up and go down, they'll slowly, this intensity indicator will slowly go down the waterfall, which is why it's called a waterfall display. So in this case, we've got one that was very strong a couple seconds ago, but he's been off the air for a few seconds. But you can see that's where it was. Now, if you're in a contesting environment, you say, there's a station there I might be able to get. So you might want to listen there. And if that person comes back, you'll work him in the contest. So time is vertical. So we see the signal slowly falling. We can see a little bit of history going on there. And then signal strength is intensity. So these red, very strong signals. So horizontal, frequency. Time is vertical. Signal strength is intensity. And here's the actual pool question. What describes a waterfall display? Frequency is horizontal. Signal strength is intensity.
And it should be time is vertical.
Yeah, time is vertical. Okay. I just did this correction today, so time is vertical. All right, we'll fix that. All right, and then on to the questions. What of the following is a way to establish contact with a digital messaging system gateway station?
Delta.
Transmit a connect message on the station's published frequency. On what bands may automatically controlled stations transmit radio or data emissions, transmitting radio or data emissions communicate with other automatically controlled digital stations?
Delta.
Delta.
Yep, 6 meters and up. What is required to conduct communications with a digital station operating under automatic control outside the automatic control band segments?
Alpha.
That's alpha. Yep, there has to be a control operator can control because you're transmitting it in an area where the FCC wouldn't expect you to pop up. Under what conditions are messages that are sent via digital modes exempt from Part 97 that apply to other modes of communications?
Alpha.
Alpha. Can't do it. And then what symptoms may result from other signals interfering with a PACTOR or VARA transmission?
Delta.
Delta.
Yep, remember all three of those we talked about. Then what action results from a failure to exchange information due to excessive transmission attempts when using an ARQ mode?
Bravo.
Bravo.
Yep, eventually the connection is dropped, bravo. Which of the following describes a waterfall display? And this one you've got to think about and read carefully. And I hope you're the first class that's going to get it right on the first try.
Charlie.
You got it right, yay! Even though I had that word wrong on my slide. You guys are so awesome, and gals. We haven't heard too much from our ladies tonight, but I know you're listening. Now, we're basically at the end of our time. I'm going to flip through these super fast, and then you'll get all of the information in the handout tomorrow. So the first thing, new generals really need to get on the air. I'll a lot of times look people up on QRZ, and I'll see that there's the number of times they've been looked up is under 100. Those people aren't on the air. So we need for you folks to get on the air. FT8 is a great way to do it. Lots of contacts, it's fun. DX is exciting. You can do it with a beginner HF station. No beams or expensive stuff. You can do all of these awards, just like I did from a compromised station. We know it's not a conversation mode. A little bit more of where it came from. So we've talked about it a little bit. This is interesting. This is from about a year ago, but during a 2-hour period, there were 3 million contacts recorded using FT8, and then you can see how they spin down with all of the other modes. So by far, the greatest used mode in ham radio today. We'll just kind of skip over this. It shows the 3 programs that we use. Ham Radio for Dummies. Okay, this is somebody that I looked up while I was working, and that was his picture. It's an example of a DX contact. This is PSK Reporter. Once you're on FT8 for a very short amount of time, you can go to PSK Reporter and see where you were heard in the world. Very cool. the DX contact to Africa, getting started. All you need is a transceiver and a radio if the transceiver has an internal sound card. A little bit more about getting started. This is the setup that I use. FT8, or the software, JT Alert, which is an accessory program. It automatically goes to QRZ-COM. It automatically logs to my logging software and automatically uploads to Logbook of the World and Club Log. So all of this can be configured. This is where you can get the software. A little more on software. Encouraging people to get a Logbook of the World account. And really important, find somebody that's doing this, because configuring all this stuff can be a little tricky. So find an Elmer, somebody that can help you. That's the best. Be sitting side by side. I have helped people remotely, but it's a lot harder. And then the release notes and so forth. And then our Gary Hinson tip here that I shared earlier. There's forums out there that are available. And look at that in more detail when you have a chance. So that's all we have for tonight. Today was chapter 6. What are we doing next week, Gary?
My remote control software died at the very end.
Were you in automatic control?
So some folks have observed that when I typed in tonight's show, I said chapter 7. That's a typo.
Oh.
Chapter 6 was tonight. Chapter 7 is next week, but I think you're going to want to be here because it's antennas. And everybody wants to know about antennas and feed lines, and it's something that we're all involved in. So that's next week. Thank you all for being here. I appreciate it very much. Dave, anything else?
Nope, nothing here. We're going to go ahead and close it down, but if anybody in the Zoom class has questions, we'll hang around for a bit and talk to you.
All righty. So y'all on YouTube.
Yep.
73.
73, y'all.
Great job.
Yep. Thanks.
Question?
Sure.